Hello everyone. In this video, we are going to solve the AXI4-Stream homework problem from the previous lesson. The goal is to design a Verilog module that receives an AXI4-Stream burst and saves the received data in memory. After the receiver code has been explained, we will simulate the design with a test bench to verify that it works. Then, we will demonstrate the receiver working in a complete block design. Before watching this video, I recommend watching the previous lesson and attempting the homework problem yourself. The previous lesson explains how AXI4-Stream transfers work. Alright, let's get started. So this here is the homework problem that was assigned last video. The goal was to design a Verilog module that receives 16 values using AXI4-Stream and stores those values into internal memory. Before building the receiver module, let's review how AXI4-Stream works. When a Verilog module receives a list of numbers using AXI4-Stream, the Verilog module uses the pink signals as inputs and the green signal as an output. It does so by using the following rules. First, the receiver starts with t-ready equal to 0. This means the receiver is not accepting data yet. Second, when the receiver is ready to process an incoming stream, it sets t-ready equal to 1. Third, if t-valid is equal to 0, then the transmitter is not sending valid data, so the receiver does nothing. Fourth, if t-valid is equal to 1 and t-ready is equal to 1, then the receiver captures t-data on the rising edge of the clock and increments the data index. Fifth, if t-valid is equal to 1, t-ready is equal to 1, and t-last is equal to 1, then the receiver captures the final value and ends the stream. Now let's explain the receiver code. In lines 1 to 14, we declare the module ports. The important AXI4-Stream signals are in lines 5 to 8. The S_axis prefix is important because it helps Vivado recognize these 4 signals as one AXI4-Stream bus when we package the IP. If we use signal names that Vivado does not recognize, the IP packager may not automatically identify them as being part of an AXI4-Stream bus. In that case, we would need to wire each signal manually in the block design. The S_axis_T data signal was set to be 32 bits wide because the AXI4-Stream FIFO sends 32-bit data. However, this receiver only stores 8-bit numbers, so we only use the 8 lower bits. The switches and LED ports are declared on lines 10 and 11. They were added so that during the hardware demo, we can select one of the 16 memory locations and view the stored value on the LEDs. On lines 16 to 18, we declare the internal memory, the index, and a variable. On line 23, we assign the S_axis_T-ready to the active low reset. We do this because the active low reset is going to get hardwired to 1. On line 27, we assign the LEDs to display the memory location selected by the switches. On lines 30 to 41, the reset logic is defined. On lines 50 to 52, Rule 3 is enforced since the logic ensures nothing happens when t-valid is 0. On lines 55 to 73, the main logic is defined. On line 59, data is saved when both the required signals are high. Then lines 63 to 71 ensure that the index is always set to the correct value. So this here is the simulation. As you can clearly see, every time the test bench simulates a burst of numbers coming in through the AXI4-Stream bus, the Verilog module correctly saves all of the numbers into its internal memory locations. The source file and test bench needed to follow along are provided in the project files. To test if the receiver works, we will use the following setup. First, the processor will send 16 numbers into a FIFO using AXI4 write commands. Second, the processor will send a command telling the FIFO to transmit the numbers using AXI4-Stream. Third, the receiver that we made will receive the AXI4-Stream. Fourth, we can then flip the switches and observe the LEDs to verify if the correct values were received. I will not show how to set up the block diagram because the steps are very simple. All you need to do is add in the FIFO IP block and add in the receiver IP after packaging it. Then after that, you just generate the bitstream and export the hardware to Vitis. So this here is the demonstration. I have already programmed the FPGA in Vivado. I have also already set up the run configuration and built the Vitis code by pressing the hammer icon. All of those setup steps were covered in the previous lessons, so they will not be covered again here. When we program the device, we need to check that the LEDs always show the value that corresponds to the switch setting. If the LEDs show the correct value for each switch position, then we know the receiver is working. If you change line 14 of the code, then the LEDs should show the updated values after rerunning the code. This is my FPGA after running the code. As you can clearly see, the LEDs are showing the correct values, which means that the entire system is working as intended. I recommend downloading the code from the project files and running the experiment yourself. You can also change the values on line 14 and rerun the code to see the LEDs update with the new values. Alright, that's all for this video. Looking forward to seeing you in the next one.